The next section of this course is called kinetics, and the kinetics of particles, now we're really getting into the study of the forces. So far what we've done is we've looked at position, velocity, and acceleration. And we've looked at how you move between them. And we've looked at it in different coordinate systems. But the motion has to come from somewhere. And the motion actually comes from, the way that we derive this in the real world is we get the acceleration from Newton's second law. So this acceleration is actually coming from the summation of forces is equal to mass times acceleration. This is Newton's second law. So in this chapter, what we do is we look at the summation of the forces. We look at what's happening. From that, we find what the acceleration is. And then once we know what the acceleration is, we plug that back into the same calculations we were doing before, and we can find velocity and position. You could also start potentially with an acceleration, and then the question's asking you to find what the forces would be. In the previous chapters, we talked about how the particles don't have any dimensions. So we said we could still treat an airplane as a particle because we're not looking at the rotation of the airplane itself. But just even though we're dealing with particles, our particles still have a mass. And the forces are proportional to the mass times the acceleration. So the particles that we're using, particles have no dimensions, but they do have mass. In your next course, you'll be dealing with rigid bodies, which is where you consider the dimensions of what you're analyzing. A quick note about Newton's second law. This only applies in inertial reference frames. Inertial reference frames mean constant velocity. Technically, for our problems, if we have a reference frame that's connected to the Earth, technically the Earth has an acceleration, but we negate it for these problems so that, because the math works out close enough, and so it's just an assumption that we make that the Earth, if your coordinate system is attached to the Earth, that means that it's an inertial reference frame. In kinematics, we weren't super fussy with units because oftentimes if we had, let's say our x was given in terms of millimeters, then we could just give the velocity in terms of millimeters per second and it wasn't a problem. But in kinetics, you have to be a lot more careful because you're dealing with forces. And so your units, just have to be more aware of what your units are doing. So it's really important in kinetics that your length is in meters or inches. So this would be imperial units, and this would be metric. Your time should be in seconds always. Your mass should be in kilograms for metric or slug for imperial. And your force should be in newtons for metric and pounds for imperial. And then your gravity is 9.81 meters per second squared or 32.2 feet per second squared. So this whole chapter really revolves around this equation here. I'm going to move the screen up. So we have the summation of the forces is equal to mass times acceleration. Notice here that forces are also vectors. We have the arrow here, our forces are also vectors. So when we're doing drawings in kinetics, you actually do a drawing for both sides of the equation. So you'll have, on this side, this is called a free body diagram. And on this side you have what's called a kinetic diagram. You need to draw both of these for all the problems. Let's say you have a box and there's a force being applied to the box at some angle here. This is your force. Then you'd also have a weight of the box coming down. You'd have a normal force going upwards, and then you might also even have some friction. You'd have some friction force pushing against you. This here is your free body diagram. This is your drawing that denotes all of the forces acting on your particle. Your kinetic diagram is showing the acceleration. So this box, I didn't draw it, but this box was on the ground here. So when you apply that force, stay on the ground here, your box is going to be accelerating in this direction. So you have a mass of the box times the acceleration in the x direction, or even just acceleration here, or just ma. This here is your kinetic diagram. I'm going to move the screen up. So now if we were to write out this back in the form of an equation, we could write it how we had before. So we had summation of F is equal to mass times acceleration. We could also write this as the summation of the force x in the I direction plus the summation of Fy in the j direction plus summation of Fz in the k direction is equal to the mass times the acceleration xi plus ayj plus azk. So here, this here is the vector equation expressed in Cartesian coordinates or rectangular coordinates. So we've changed it. Here the acceleration and the forces were vectors. When you break them down into the components, they've gone and they've turned into scalars, exactly the same as we had in the previous chapter. You could also write this out and just separate it as three equations. So you have summation of fx equals max, summation of fy is equal to may, and summation of fz is equal to maz. So here we have 1, 2, 3 notations. These all capture the same amount of information, but it's in a different form. Solving problems in this chapter follows a pretty similar flow, so I'm going to move this up and we'll go through that. So if you're solving problems, the first step is to choose your coordinate system. Remember how we had three coordinate systems in kinematics. We had rectangular, so we're talking xy, normal tangential, or polar coordinates. All of those coordinate systems still apply, so you have to choose the one that you want to use. The next step is to draw your free body diagrams and your kinetic diagrams. Make sure that you're defining positive directions. This is really important. Some problems you have to do what's called impending motion analysis. So if mu s is given, do impending motion analysis. What this is saying is, if I use the same example as before, we had the box and we had a force here, and remember we showed some friction moving against the box. If the force being applied here is not enough to overcome that frictional force, then the box doesn't move and you have no acceleration. If it is enough, then you do have that acceleration. So sometimes you're given mu s, this is your static coefficient of friction. This is normally it's normally a larger number, and that's the friction it takes to start the movement. And then mu k represents the friction, kinetic friction, so there's actually less of a force once the box is moving. So just make sure if it doesn't tell you that the system's moving, you have to start off with impending motion analysis. The next step is to consider any forces due to springs. So you could have force of a spring is equal to k times delta x. This is the change in length. We'll get into that in another example. Once you have drawn your free body diagram and your kinetic diagram and all of your forces are denoted, just a quick note here, your free body diagram is external forces only. And we'll get into that again when we go through free body diagrams more closely. Then you apply your equations of motion. And you want to do this in the scalar form. So by that I mean you want to do summation of fx is equal to whatever, and then the summation of fy is equal to whatever. Then you solve these equations. And then you apply any necessary kinematics equations. So from these equations, from your equations of motion, the output that you'll get will be accelerations. From there, the question might say, what's the position of the particle? Then you apply those kinematics equations that we've been practicing up to this point. So that's pretty much the stages, but we'll go through some of those specific cases in the next videos.